It's my pleasure to introduce to you Yurii Moroz from Enamine, and just a couple of points before we actually get started today. Because we have close to 100 people attending, you are all muted. Otherwise, it would be very noisy on the line. So for communication, please use this very chat box that you already used to answer my request about the audio. We will pick up the questions at your convenience after the presentation, or if it is important at the moment, even throughout the presentation. So no question will be lost. At the latest, you hear about it after the presentation finished. And you don't have to frantically take notes. We record this webinar and put the recording on our web page, as you see it stated here. So sit back, relax, and enjoy the flights, as people from Lufthansa say. A few words of introduction for our guest speaker today, Dr. Yurii Moroz again. He received his PhD from the University of Kiev in the Ukraine, and afterwards went to a postdoc at two universities in the US, both Tufts and Syracuse University. And then in 2014 took on his position that he still has now, or where he still is now today, namely scientific advisor at Enamine. And his goal is to deliver new molecules to the drug discovery community. And I think you hear more about this throughout the presentation. Yurii is well versed in this topic. He has co-authored over 40 scientific publications by now. Now that we introduced the speaker, I would actually like to ask you for a little bit of feedback as well. For that matter, I prepared a little poll here. This is giving us information about your background, what's your training, and what's your current position. This helps us give the presentation just the right twist for the audience, and also it is nicer while we are all speaking to our monitors here to know at least the audience a little bit better. Okay, I see the poll answers are coming in. Maybe a few more clicks. That is very nice. Okay, we are reaching 90%, and I'm closing the poll in 5, 4, 3, 2, 1 now. And showing you the results is, as you can see, the majority, almost half of the audience are computational chemists, closely followed by medicinal chemists, and also very nicely also a few people from the other disciplines. Again, thanks a lot for sharing with us your background, and with that we now come to the presentation. Wait a second, I need to switch here to Yurii's slides now. Okay, right. Yurii, give it a start. Welcome.
Welcome everybody. Thank you for joining us at the webinar. And Christian, thank you for such a kind introduction. So today we'll talk about the REAL Space Navigator. That's the software tool jointly developed by Enamine and BioSolveIT. And the tool allows, at least in the current version, to explore a chemical space of around 650 million synthetically feasible molecules. Christian?
Yeah, this is just stating that what we present today is actually the outcome of a joint venture between Enamine and BioSolveIT. And those who have attended a couple of webinars here from BioSolveIT know us very well by now. For the others, we are a software company. We have 20 software developers here in St. Augustin in Germany located, and we consider our core competence to produce software that is aiming at fast, visual, and easy to use as the key criteria, and we are active in the areas structure-based, ligand-based, and fragment-based drug discovery or lead discovery.
Okay, so as for Enamine, Enamine is a contract research organization with the main facilities located in Kiev, Ukraine. It has 600 chemists, 10 its own newly built buildings. Current stock collection is over 2.5 million compounds, and now Enamine has a biology services that can do HTS, ADME, and studies in animals. Christian?
Yeah, so in order to motivate what we present today, imagine you could find anything in a huge chemical space. And what I mean by anything is I'm going to elaborate on a little further. It's not just some pre-collected, pre-sampled, whatever entity, but it's really locating anything. Secondly, we want to make accessible sort of distance searching. I mean, everybody knows that similarity is a very key concept in chemistry and also particularly in ligand-based drug discovery. But we all also know that just mere analogues are kind of boring. So we want to locate something in this huge chemical space that is distant yet alike. And what I mean by this statement here, again, I'm going to elaborate on further down the line. And last but not least, just discovering things in the space, something distant yet alike, is not enough, so to speak. It should be interesting, really. So from the perspective of the target at hand. And most importantly, and differentiating from other de novo approaches, it must be something readily available. So not just some theoretical concept, but compounds that can really be made. And I'm confident that we can share with you today that along these three goals, we aligned the development in this joint venture, and that we are going to deliver and share with you today.
Okay, and Christian just talked about huge chemical space, and to build this chemical space you need building blocks, the reagents, and the reactions or the rules how to build them. For Enamine, now it has more than 45 billion blocks in stock, and every month more than 2,000 new building blocks are delivered. To make this space, you need, as I mentioned, the reactions, and typically those are parallel chemistry procedures. For Enamine, that's almost 150 procedures available now. All this creates, we can call it Enamine universe. Christian? Okay, so that's basically Enamine universe that now encompasses more than, well, a lot of billions of molecules. But obviously, those are just molecules, virtual molecules, and people are interested in to select the space of feasible molecules, the molecules that can be accessed, readily accessed. And this space we called real space. Okay, so Enamine real space is based on validated chemistry and qualified reagents. All this supports high feasibility success rate and relatively short synthesis time. To explore the space, we have been established two tools. Christian? Okay, so one of them is actually Enamine real database of over 330 million molecules. It contains classical structures, chemical structures. Another tool that we would like to present today is actually the Navigator. That's a software tool. That's not a database. Next. A few words about the actually validated chemistry and qualified reagents. So under validated chemistry, we mean that each procedure before included in the space is actually validated. Well, it's validated in at least 1,000 experiments, and for example, this reaction on top, you can see that it's validated in more than 9,000 experiments, and success rate for this reaction is really high, 83%, along with the yield. 35% is actually a good yield for parallel chemistry procedures. And this kind of criteria allows us to include the above procedure in the enumeration to create the real space. As for the procedure below, you can see that number of experiments that are taken is not that big now, and it's not enough at least to say that whether it's validated or not. The overall success rate is not also very good. That means that this procedure needs some modification to the conditions, and hopefully in the future it can be included in real space. As for the products, you can see that the procedure on top is actually can give you around 3,000 products, fully enumerated products, while the bottom procedure can give you over 2 billion products. Next slide. Okay, so as I mentioned before, we validate the procedures and the reagents. Each reagent, a new reagent that is delivered from our chemistry lab, it proceeds through different validation processes. One of them is actually include them in a set of typical reactions. For example, for this aldehyde, we have reductive amination reactions. And if we see that success rate with this aldehyde and the different counterparts is high, for example, for the aldehyde on top, it's 81%. We will include this reagent in the enumeration. For the aldehyde on the bottom, the success rate is very low. So this aldehyde is not included in the enumeration. In this way, we eliminate the structures with low feasibility. Next. Okay. So the real space now the highly feasible real space, is created out of 106 high-score validated reaction procedures and almost 55,000 high-score qualified in-stock building blocks. All this allows us to access the space of around 650 million molecules. Those are feasible molecules, and they're not enumerated. Next. And this is just a comparison table that can give you some idea what actually differences and similarities of the real database and the space accessed by the navigator are. So in real database, we have the enumerated molecules shown as smiles. But for in Real Space Navigator, there is no final enumerated molecules. There are just rules, reactions, and syntons that undergo those reactions. And basically, the final molecules are generated in silico, generated as similars or similar molecules to the query molecule. The size of Space Navigator accessed space is actually 650 million, and the real database is now around 340 million molecules. The difference between the size is probably based on the filters applied for real database. Historically, real database was built from drug-like molecules, but now we've seen the trend to the lead-like space. So the newly enumerated molecules are lead-like, not the drug-like. While the Real Space Navigator has no limits to the structures, and we can find molecules there as large as 1,000 Daltons. There is difference in reaction protocols involved in both spaces. For real database, we have 122 reaction protocols, high score and low score, because we know how to handle them. While for a Real Space Navigator, we included only high score protocol, at least in this version. The same with the building blocks. Real database has both high score and low score building blocks. For Real Space Navigator, we have only high score building blocks. This is done just because for a Real Space Navigator, we would like to avoid combinations of low score and low score building blocks. While for real database, low score and low score is not possible just because of the way it's built. Both databases are built on the building blocks that at least 10 grams in stock available. That means that, for example, if in few months, if you have a database that is few months old and you want to get the compound from the database, you can be sure that the building block to make this compound is still available. Okay, next slide. All right, so current version of Real Space Navigator is 650 million approximately. But as I mentioned before, we have much more reactions we can include, as well as the building blocks. And in the next version, we expect to see the billions of molecules.
Yeah, it should be stated here that what you see here currently and also on our web pages, that's the very first version of the Real Space Navigator. I guess all we want to point out here is there's lots of opportunity to grow this space even further. Okay, now it's my turn to tell you a little bit about the search engine underneath. You have heard already that the Real Space Navigator comprises data, namely the space. So that's reaction protocols or reaction procedures and building blocks. And we don't enumerate the molecules, but we search for molecules on the fly in the space. And how these searches are done, I'm explaining to you on the next few slides in more detail. Okay, so consider two molecules. On the left-hand side here, a query molecule taken from a PDB structure. And on the other side, you see a virtual hit. First of all, I show you the representation of the molecule. Yeah? We call this representation feature trees. Like the name suggests, a tree-like topological graph that connects nodes with colors, and these colors have obviously meanings. The meaning is the respective property. So it's a quite abstract description of the molecule. Here, for example, this node representing this substructure here on the molecule, you will see in a second in more clarity, represents a ring with acceptors and donors, and it is aromatic. It is in a ring, and it has a certain spatial volume. And another node here representing this SO2 group, of course, two strong acceptors and a little bit of pi electrons here in the bar for the aromaticity. It's not in a ring, and it also covers a certain spatial volume. I think the representation becomes clearer when I overlay them to the molecules. Okay, given this representation as a topological graph with pharmacophore style properties, if you want, we can now calculate a mapping of the nodes from one tree onto the nodes of the other tree. This is a little bit like sequence alignment, except these are not strict sequences, but they have branches. But otherwise it's fairly similar. Gaps and insertions are the typical things that can vary from mapping to mapping. And from all mappings, the feature tree software generates the mapping with the overall highest similarity. So given the nodes from one tree mapped to the nodes on the other tree, we compare the local properties, and then we build the global average, and that is the overall similarity. It's 0.81 for these two molecules. And aside of just this similarity value, which we can use for database screening, for example, we can actually use it in a visualization of the results. So we can color code the mapping on the structures and see, okay, this ring here is mapped onto this ring, that ring onto that, and so on and so forth. And interestingly, this ring here is actually mapped onto an open chain part of the virtual hit. And that mapping leads to that maximum similarity of 0.81. And you can imagine further, once you have a mapping, you can enumerate easily conformers and then map the features on top of each other, and thereby gain quick access to a 3D alignment even. So the search engine behind is based on these rough descriptors, pharmacophore style descriptors. It has nothing to do with 3D. It is just a topological descriptor. It gives you a similarity value. It gives you also the mapping, which you can use here in this color-coded pictures. And you can even take it further to calculate a 3D alignment. And this search method works also for the searches in the spaces, not only with enumerated molecules. And that is what we put together. We put together the real space that Yurii just described with over half a billion virtual compounds. And then as a first benchmark, we took approved drugs and tried to locate molecules similar to those approved drugs in the real space. So that was from some database which we found in the web, 709 FDA approved drugs that are at the same time rule of 5 compliant, so not too big and stuff like that, so that we have a realistic chance to find them. Actually, we didn't want to search for biologics here, but for small molecules instead. So we took each of the FDA approved drugs in turn, searched every one in the space using the feature tree similarity search, and this here is the statistics. So you see that we find similar molecules, to a high degree similar molecules. For the most part, the peak of similarity is actually 0.97. So that is quite similar to the query molecule. And as this red graph overlaid, you find an accumulated hit rate. And that shows you that with 0.88 similarity, we pretty much find every one of the 709 FDA approved drugs. So that is not saying that we find those drugs themselves. Only a fraction of them can be found with similarity 1. But for every one of them, we find a similar compound to the degree of 0.88. But aside of this coverage of the space, we found out the software is really very robust. All queries could be processed. We didn't have any issues. Remember, this is the very first version of the space coupled to these searches. The speed is quite high. On a standard PC, a search takes between 1 and 2 minutes, mostly 1 minute per search. The time depends on the size of the query molecule. And again, this is an average. And as I stated before, we have pretty good coverage. The median of similarities is 0.96, so quite high. A lot of these molecules are reflected in some way. Now that you know the contents, namely what the space is made of, the search engine, so how you access things in the space, how is it with practical access? Well, we built interfaces to several software packages. On the one hand side, there's the search node in Pipeline Pilot, where this search engine runs underneath. You simply tell the Pipeline Pilot node where the space is located. You drop in a query, run it, and take a look at the results. Similarly, in KNIME, you can draw or import your query molecule somehow, the same search node, you tell it where the space is located, and then it runs for 1 to 2 minutes, and then you can look at the results. For convenience of users without access to these workflow packages, we specifically built a small graphical user interface, and that is what we termed the Real Space Navigator. With all these search or access options, it's important to state that all of this runs behind your firewall. Yeah? So you download the space, and then you run the searches behind your firewall, so it's in complete safety. A few more words about the graphical interface. Once you've installed it, you double click on the icon on your desktop to launch the GUI, and you see it's quite minimalistic. It has a query side and a results side. You feed in a query, you have multiple alternatives, loaded by file, drag and drop, or copy paste from the clipboard. So all very easy, particularly the last one. You can use your favorite drawing program, Control-C, Control-V, to drop it here and get this kind of picture. The button is enabled now to run the actual search. You see the query underneath, and there is just one parameter that you can tune, whether you want to have more similar compounds or more surprises in your hit list. When you turn it more to the left, then on purpose we don't try to locate the most similar molecules. So fewer analogues if you want, but aim at compounds with a little bit lower similarity so that you see more scaffold hops and more surprises in that sense. Okay, 1 or 2 minutes later, the result list here is populated. You have these usual checkboxes. You see the similarity value. You can also sort by similarity value. Later on, we may sort by other properties and elaborate the GUI a little more. But for now, we deemed it sufficient for you to just simply make your selection and then export, and either you post-process such an export, which is just a plain SDF file further, or you send it to Enamine to request a quote and actually ask for those molecules. So it's really very simple from the installation to the use. It's meant to be easy access to this resource.
Yeah. As for the delivery actual molecules, we expect the success rate of 80% for the libraries of 100, 150 compounds, and the synthesis time here is 3 weeks. A few words about the ordering. Cherry picking is enabled for the compounds from Real Space, so you don't need to select the actual enumerated rows. Exclusive supply possible, and the price is fixed for all real compounds. It depends on the number and the amounts in the order. For more information, please contact Enamine at libraries@enamine.net. And now, Christian, I think it's the last slide. Yes, so I would like to thank you for your attention, and hopefully you will enjoy using our joint product.
Yes, I have just one more request now to your side. The second poll today, and also the last poll. I'm not going to bother you any further, but having seen now Real Space Navigator, we would like to hear from you what should come next. Yeah? What is most important to you from these given proposals? Namely, do you want us to make the space bigger? Do you want to be able to combine your own in-house building blocks somehow with the space, or do you want to have easier access also for structure-based projects? Essentially give a PDB and let the software run and find something that docks well into a given active site? Or do you want to have other ways of searching, like a substructure search, something that you are more familiar with, like a fingerprint search or so? Give us your votes, please, on what you consider most important. This has an influence on our priorities for further development. Okay, thanks a lot for all these votes coming in. I'll wait for a few more clicks. It's a complicated poll, so I give you a little bit more time. And I'm going to close this poll in 5, 4, 3, 2, 1 now. Okay, and showing you the results. Apparently, working also in the structure-based world appears most important, or easy access also to the structure-based searches. That is interesting, and more familiar ways of searching, like a substructure search, maybe to carve out also a subspace is second, followed by other searches. Thanks a lot. This is very helpful for us. And with that, I formally finished the presentation. Thanks for joining today's webinar. As I said, we will come to the questions that we got in a minute. Just for those of you who need to leave right away, you may or may not have noticed that we put Real Space Navigator, that is the GUI that I also presented, on our webpage. 650 million compounds available on demand, and searches possible within a minute or two. We hope to have whetted your appetite and that you start now explore this huge resource for yourself, and save the date also for our next webinar next month. It's actually March 23rd, where we focus on CISA for more efficiency in drug discovery. I hope that you and your colleagues will join us there as well. And now, with that, I close the presentation part.